Testing, 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 testing. Just about here. Let's see how we're doing. Kind of fuzzy today. Good. Right. Question. Could I show you how the diff function works again? Yeah. It's a command, not a function, first of all. I know that seems like an academic distinction, but, you know, this is an academic course, so academic distinctions are to be expected. So let's go topic 9. Should be some files in there we can diff. Code. See? So, take, for example, the sums and products C source code files, right? Cat sums.c. There we go. That's what it looks like. Cat products.c. That's what it looks like. Diff sums.c products.c. That gives you a itemized report of all of the differences between these two files. So notice this line and this line are, although they're very similar, they are different. This line has a difference, this line has a difference, but these two lines do not. So the difference is indicated on the lines that have differences. And that's all that difference does. It just does a line-by-line comparison of two files, and it tells you what about them is different. The interesting bit is when you start piping in standard output or standard input to be able to, you know, if you've got standard output and you pipe that to a file, then you can apply diff to it. So, yes. But, yes. Anyway, hello all 8 of you. Good morning, oh fancy meat computers. We're going to learn stuff about electronic computers today, as is typically the case when we study things. You know this class. You know we talk about computers and junk. So let's take a look. We are talking about topic 10 today. Boop. There we go. So how did you guys find the lab yesterday? There were some people who were concerned that it might be difficult. Did you find it to be difficult, or was it super cash? I'm hoping at least a couple of you go to the lab sessions. Okay. Okay. So what about it was difficult then? Good. I'm glad that at least one person goes to the lab sessions. At least two people go to the lab sessions. Part 1. Oh, that's the bit where you, yeah. Where you have to make the code do the stuff. Yeah. You probably are overthinking it because, yeah. Syntax errors are just the programmer's bane. Well, couldn't get some of part 1. Figuring out how to access other folders in the makefile. Ah! Well, if you figured that out, then congratulations. If you didn't, all you have to do is append the directory path to the, all you have to do is include the directory path in the file name, and then it'll do the addressing, right? Yeah. Well, you guys have some more time to work that out. So, yep. We should get on with our lecture for today, though, because we've got a lot to get through and not a lot of time to get through it. So, okay. So let's say just for the sake of interest, you wanted to copy something out of the directory above this directory into this directory, right? It would be like cp ... which is the directory above, right? If you hit tab, you can see all of the stuff that's in that directory. And let's say I just wanted to copy, like, let's say I wanted to go one more level up. Sure, let's say I wanted to go into topic 2 and take a look in there. Let's say meme.png, and then copy it into the current folder. And then you can see that the meme.png file did in fact make it into the current folder. So you see, you can navigate the entire directory structure just by just by including the full relative file path in the file name argument. 1.3, you say? Well, yeah, that's you have to figure out how to pass this all of the stuff that ends up in argv into a separate array, and then pass that separate array to the library function. But yeah, this is the type of stuff that if you had a physical in-lab lab, then this would be, your TA is supposed to help you with this stuff. So, anyway. And, the TA is also supposed to help you with this kind of stuff, when it's virtual. But anyway, so let's talk about topic 10. Strings, formatting, and file I/O. We're going to talk about converting to and from strings. We're going to talk about how to manipulate strings. We're going to talk about advanced formatting options. And we're going to talk about the actual file I/O. So, just a quick recap. Remember that strings are character arrays which are null terminated, right? So when you have a string that is encoded in C, each one of these characters occupies one char-sized segment of memory, and you have one extra one, which is always there, which is always implicit, called the null character. So the reason the null character is there, if you've noticed, like working with integer arrays so far, knowing how big the array is absolutely critical to the correct processing of the memory. With strings, just because this is the way they decided to do it, they include that null terminating character so that any program that reads a string can know when the string ends without needing to be passed the length of that string at the same time, right? So, that's not a thing you see in integer arrays, but it's certainly a thing you see in character arrays. So remember, all strings are arrays of characters which have a bit width of 1 byte, right? Strings are delimited with double quotes, and characters are delimited with single quotes. That's, again, this is different from Python, because in Python, it doesn't matter whether you use single or double quotes, but in C, double quotes are strings, single quotes are characters. So, the null character has a very important function in C. You may notice that C does not know... I have this terrible habit of jumping ahead of my slides. You may notice that C does not know when an array ends, although it always knows when it begins, because it has a pointer to the beginning. That's what the array is. It's a pointer to the first element in the array. The null character /0 is used to indicate the end of a string in all standard library functions. Incidentally, it's a terrible idea to put the null character in the middle of a string yourself by escaping 0, because then all of your standard library functions will think that that's the end of the string when that's not the end of the string. Using the fact of null termination in your own code is also a very good idea. A common pitfall is not allocating enough space in your character array for the null character. So, for example, if I initialized this array to have 3 characters in it, you might, if you didn't know about null termination, that would make sense to you, because I've got 3 characters here, I ask for 3 characters there. But you have to have 4 characters, because the null character, although it is null, it is not nothing. It does not exist, although we call it null. It occupies space, and that space must be allocated to it. If a string is missing its null character, the functions in the standard string library will continue operating into memory space not allocated to the character array. Basically, you have removed the stopping condition for the loops that they use in the standard library, so they'll just continue on forever. And that, my friends, is a guaranteed segfault. Guaranteed segfault, because it will just keep going. Well, actually no, because the null character itself is all zeros interpreted as a character, right? It has an integer value of 0. So as soon as one of these functions hits a memory segment that has all zeros, it'll stop there, but that'll be beyond the string that you want to work with, certainly, and you have a high probability of producing a segfault with this kind of stuff, with this type of behavior. This is what we call, this is what we were talking about when we were talking about dangerous programming. This, yes. Also, this will introduce smelly garbage data into your program and may even cause a segfault. So the problem that you have when you read memory that hasn't been allocated to you is even if it doesn't segfault, the values that you're reading into your program are going to be garbage data. And, the oldest of programming maxims is garbage in, garbage out. So if you put the garbage in, you will certainly get the garbage out. So, this being said, you may at this point be wondering, in Python it's relatively easy to convert a string into some other data type, right? You just use the name of that data type as a type conversion, right? With strings, it's a little bit more tricky. but you have some standard libraries available. Standardlib.h contains a certain number of definitions for string to other data type conversions. For example, string to D, str2d, which converts decimal numbers to double precision floating point numbers, or doubles. It's typical to use doubles instead of floats, but, you know. Neither here nor there, really. So, string to double takes two parameters. It takes a pointer to the string, and it takes a double pointer called end pointer. str is a pointer to the string to be converted, leading white space is ignored, and end pointer is the address where str2d stores the address of the character that it stopped on. So this means that end pointer is an implicit return value, right? This is how a lot of these functions in the string, a lot of the functions we're going to be talking about today use pointers to produce implicit return values from functions. Now, we talked about pointers last week, and hopefully you've had some time to play with them a little bit. So end pointer, basically the way that this works, right, is we give two pointers to character arrays to string to D, right? The first one is the string itself, obviously. The second one, we actually give it the address of a pointer, right? When string to D is finished, whatever character it stopped on, it'll take that address and store it inside that second pointer that we gave it, inside the memory address that corresponds to the second pointer that we gave it. So in effect, in addition to the actual double value, which is returned from the function as its direct return value, you have this secondary return value which is being used. So, string to D converts as much of the string as it can to a double format, and then returns that double. This is an example of a function using pointers to, in effect, return two values. So, it seems to me we would have a example. Let's see what we got here. Aha. That is a lot of stuff that we haven't done yet. So, where am I here? Let's get into the topic we're actually doing, eh? Topic 10. Code cat or touch conversions.c. Get it conversions.c. So, if you have any questions, this would be a good time to ask them as well. Include stdio.h as usual, and in this case we're also including standardlib.h. int main. We shall just have a number here, 64.168 beans, and then we'll have double val is equal to str2d buff. We'll also need a character. I forgot to type that. Character array. We'll have a character array, call it post buff, not assign it a value, and we shall give this the address of post buff. Now, if we printf buff what's the conversion for, what's the format conversion for floating point, or a double again? F. All right, we'll use E just for fun. And then, so we'll give it buff, val, and post buff. GCC conversion.c. I've got some nasty little syntax errors here. Missing array size. Let's just call it 100. Why not? Oh, what? Incompatible pointer type. Oh, all right. We'll just give it that then. Haha! We have quashed the errors. A.out. So, you can see, I forgot to include a new line. So this is our starting string. This is the number that has been read from it. And this, with the space included, the character, this new character pointer points to the middle of this guy, right? It's pointing to this character here. So if we interpret that as being a string, we get the rest of the string. That's going to be an important concept coming up. So, in a similar manner, there is str2l, which produces a long integer. There are a couple of there are some slight differences, however. But you'll notice that largely the thing is the same, right? String and pointer, those both function in the same manner, but we've got this new argument, int base. So the differences here between string to d and string to l are the return type, which is now long int, the third argument, which is the base of the number that we are interpreting. So using this, if we specify 16 as the base, then we get hexadecimal. 0 specifies either octal, decimal, or hexadecimal. Those are like the defaults, right? But if you wanted to interpret, if anybody remembers back to 1MD3, if you took it 1MD3 with me, there was a one of my favorite things to test you on, or that are in the assignments when it comes to the unit on base conversion, is trying to get you to do exotic base conversions, right? Like, what does it look like? Write an algorithm that converts like base 23 numbers or something, right? Well, you would just you would just specify 23 here, and everything would work. There are a number of conversion functions that work in a similar manner. So we've got one for doubles, floats, long ints, unsigned long ints, long ints, and unsigned long ints. Notice the absence of functions convert int and short. This is... Yeah, there we go. It is possible... yeah, well, it's a pretty good test to see if you understand the concept of bases, you know? All your base. So this is possibly it is possible to convert directly to integer using A to I. However, it's unsafe, and it's unnecessary as string to L can easily be typecast as either int or short if you need them. So, that being said, your humble professor has used A2I once or twice, and it works, and it's fine, and it's apparently dangerous, but yeah. They were fun when they worked in the end. Yeah, that's the thing. That's coding for you. Pardon me. So, okay, sure, fine. We know now how to convert strings to numeric values. But how do we convert numeric values to strings? Ho ho. It's a trick question. We've been doing it all along. Printf writes to standard output, and in order to write to standard output, it has to interpret things as a string. So, what we have now is we have a slightly different take on printf called snprintf, which writes to a specific memory address rather than defaulting to standard output. So, we have, for snprintf, we have str, string, a pointer to the memory address the characters will be written to. We have size, which sets the maximum number of characters to write. Remember to leave enough space in both the above for null termination. And every argument past the second is used in precisely the same manner as printf. So it's like printf, but it writes to a memory address instead. So let's say let's say char buff 100 value or int val is equal to some number. In the end, we will printf as a string. This is kind of dumb, of course, because you don't, like, there's no point in converting it to a string and then passing it as a string to printf. You might as well just do it in one line, but this is for the purposes of demonstration. Buff. So we'll see what's in buff. Hopefully, let's just assign the first guy to null termination, just in case this doesn't work. So, snprintf buff the size 100, and then use our handy-dandy string formatters, and there we go. Oh. Here I am forgetting my semicolons again. There you go. Everything works, everything's hunky and dory. There we go. The return value of snprintf is the size of the format string after substitution. Note that this may be distinct from the size of the string written into memory. So yes, this means that we can check to see if the string had to be truncated by comparing the size of the input to the output. So essentially, let's imagine that we were, well, we can do this, we can show this pretty easily, right? So let's take a look. What's the return value here? Let's call it int check. Let's say we only had a buffer of 5. If check is greater than 5, then we should return something, a non-zero exit status. Otherwise, we can print the thing. Because if it has to truncate, I believe it also loses the null termination. Aha. See, it didn't work. Printf. Check. Right? 8. There are 8 characters in this integer. If we have 8 characters in this integer, should it be greater than or equal to, actually? If we have 8 characters in this integer, that means that it overflowed the buffer, right? So that what C is doing is it's providing you, the programmer, a mechanism for checking to see if the buffer was overflowed. But again, as with everything else in C, you got to perform the check manually. So if I reduce the number of digits here, everything works, and we get our value printed. So there you go. Are there any questions about the foregoing material? Give me a thumbs up. Have we lost everybody yet? No? Well, at least viewership is remaining consistent these days. Oh. Could I show you the code at the end of class? Yeah. The other thing that you can do is you can always pause the video if you need to look at it a little longer. But yeah, remind me to post the code to Teams or something. So, string manipulation tactics. Data duplication with string copy. Have you ever wanted to copy a string? Well, string copy and string n copy are the functions for you. These are contained in string.h, right? So, thank you. In order to use this new set of functions that we'll be exploring, you got to include string.h. Now, string copy does exactly what it says on the box. It takes a string stored at s2 and copies it to s1. So that's like the reverse of what you might expect from the arguments, but like if you use the cp command, it's copying from the first parameter to the second parameter. In this case, it's copying from the second parameter to the first parameter, but you'll find that out quickly if you mess it up. Yes. The extra argument in string ncopy is similar to the size parameter in snprintf. String ncopy copies at most n characters. This guards against buffer overflow, making string ncopy the safe version of string copy. I'm not sure if CPP will complain at you if you use string copy instead of string ncopy, but you should get in the habit of using these buffer limited versions of these functions. Once again, you must make sure S1 is large enough to contain S2, and that n takes null termination into account. So there you go. Let's just demo this real quick. Char buff1 has 100. Char buff2 has 100. Text to be overwritten. Hello, world. Printf buff1 is equal to printf buff2 is equal to buff2 buff1 dum ba dum. String ncopy from into buff1 from buff2 and at most 50 characters. If we compile that, I forgot to, there we go. Let's just copy that up here too. So, buff1 is text to be overwritten, buff2 is hello world, and then you can see after the copy operation, they're both the same. Ta-da! Magic. Not magic. Science! So, here are some similar functions, some more functions that you may find useful that are in string.h. String cat usage is very similar to string copy, except the result is null term. You're performing a concatenation operation. So this is the equivalent of your Python plus, your plus sign operation. So string ncat. You can see that buff1 gets string 1 appended to it. This is an appending operation. It's concatenation. Very important, the null terminating character in S1 is overwritten with the first character of S2. So, if it wasn't, then essentially, as far as the string functions are concerned, that string would still be terminated at the same point, so the concatenation would do nothing, right? you might write that memory, but if your string functions can't see it, then it doesn't exist. Another one that's very, very useful is string length. It just takes a string and returns the number of characters in it, null characters excluded. So, this is somewhat similar to your len function inside of Python. Pardon me. So this one's a little bit different. We're now going to talk about how to compare strings. So string comparison. This is primarily useful for telling if two strings are the same string or if they're different strings. However, it does also tell you what the ordering of the strings would be according to lexographic ordering. So, let's see. You get implicit declaration of function string n copy when you try the code. Include string.h. Implicit declaration means that it can't find the definition for it, which means that's what it means when you try to use an undefined function in C. C doesn't assume that it's undefined because it could be defined depending on the code that you include or the object files that you include when you perform the compilation process. But yeah, if you're getting that error, that probably means you forgot to include it. So, with lexographic ordering, that's just the fancy term for dictionary ordering. So, and of course, in computers, because things are simple, what we're actually doing is we're doing lexographic ordering over the ordinal values of the characters themselves. I got you, man. I got you. So, I've talked before about how, well, I don't think I've talked about it in this class, actually. So, if you came from, I don't know. Okay, let me ask two questions. Number one, is there anybody listening who was from 1D04? And question number two, it doesn't matter because I know there are people in the class who took the engineering version, and I don't know if they did ASCII codes. If there is anybody who took 1D04, did you do ASCII codes? Because that's kind of important. So, essentially, this is the character encoding. This is the default character encoding that pretty much every computer ever uses. Although, I'm sure the Soviets had their own version of this that was slightly different and slightly inferior. But if you take a look, in the red here, these are the characters themselves. You see 0, 0, 0 is the null character. If you look at, like, A, B, C, D, E, F, G, these are all in order. They have ordinal values 65, 66, 67, etc. If you take a look at the lowercase values, these start at 97 and go all the way to 122. So when you're comparing strings for lexographic ordering, it's not like it's like dispense from your mind the idea that C even knows that it's looking at alphabetic characters. It doesn't even know that it's looking at like, C knows nothing. It doesn't even know what the character it's looking at is, right? It doesn't put it into a category. It can't tell the difference between plus and delete. It can't tell the difference between carriage return and $sign. All it knows is that 36 is more than 13. And that's how it does its ordering. So when it says lexicographic ordering, we are ordering lexigraphically over the ordinal values of the characters themselves. Now, it's just been, it just so happens that the way that ASCII characters are encoded, the order of the characters as they appear in this list aid lexicographic ordering. It's not like the letters are in random positions. So if you took strings that were just words, and you performed this lexicographic ordering over them, if you perform this string comparison over them, it will match what a dictionary says. But this is a more general system because it includes way, way, way more characters. I don't remember if you did that in 1D04. Yes! Oh, if they didn't do ASCII characters, well, okay, fine. But in Python, there's really, I'm gonna sneeze. Ugh, pardon me. In Python, there's, Python doesn't like to acknowledge that characters even exist, right? In Python, you don't deal with characters as individual values. All characters, in the C sense, are singleton lists in the Python sense. So, to some degree, it might make sense that you'd never talked about ASCII because you've been dealing in Python, and Python likes to hide things under the hood. It likes to deceive you about how computers actually work. My job is to tell you how computers actually work. And computers don't know what characters are. We know what characters are. It is through our manipulation of computers that, we are the people who impose semantic meaning on what the computer is doing. That is our relationship with the tool. The wrench doesn't know what a nut is, right? The screwdriver doesn't know what a screw is, but we use the screwdriver to screw in the screw, right? Think of a computer as that, in that manner. It's just a dead chunk of silicon. Anyway. So let's do an example. Incidentally, you can tell the ordering of these strings because the return value will be 0 if they're the same, less than 0 if S1 is less than S2, and greater than 0 if S1 is greater than S2, and greater than or less than is done according to the ASCII values of the characters using lexographic ordering, which is what I was just ranting about. So if we did string comp, and let's just printf the the integer value of the string comparison, string ncomp. There we go. 12. So 12 is greater than 0. So this guy is greater than this guy. T is greater than H. If we go back to our ASCII table, T has an ordinal value of 85. H has an ordinal value of 72. So I wonder where the 12 came from. Does this function return the difference between the ordinal values of the characters? Yes. String comp returns the difference between the ordinal values of the first pair of characters which don't match. Probably. I'd have to double check that, but I'm pretty sure that's correct. Anyway, so for all you Python programmers out there, here is a table of rough equivalencies between C functions and Python. So, str2l, that's int converting a string. snprintf, that's string converting an int. String copy is the same as copy.copy. String cat is the same as foo plus bar. String length is the same as length of foo. String comparison is equality or any of one of these greater than, less than, etc. Your comparator operations. String char is foo.index bar. So if you want to find the index at a particular string, if you want to find the index of a character within a string, this is the one. And if you want to perform something similar to the split operation in Python, you use string token. You tokenize. So I know we didn't cover all of these, but you should get the general flavor of how these work now and apply that knowledge to other functions in the library. In particular, for assignment 2, string token is very, very useful. I'm not going to hide the truth from you. There is a question in the assignment which is a bit of a doozy, and evidently, the fact that I think it's a doozy probably means that you think it's absolutely impossible. But, that's, the sort of thing that happens these days, I guess. So, this guy. Short question, but this one will probably take you a fair chunk of time. Simple expression parsing. So, essentially, this question asks you to write a function which can take something like 5 plus 7 minus 2 minus 1 and actually compute and return the value, right? And there are lots and lots of restrictions. You are restricted to integers. You're restricted to numbers that are no more than 3 characters. You're restricted to the following operators. You don't need to worry about hexadecimals or prefixes or postfixes or negative numbers. But you do have to account for variables amounts of blank space between the characters. So that question, you can do it the easy way or you can do it the hard way. The easy way is to use this stuff. The hard way is to reprogram all of the functionality that's contained in all of these functions yourself. Yes. Yeah. String token is extremely useful. So let's talk about generalizing this, right? Given that in C, data types are, as a concept, somewhat ephemeral, a data type is only interesting insofar as it gives the compiler a byte width to know what to do with stuff, to know how to process stuff. It should be the case that the above operation on char stars, or character pointers, or strings, should be reasonably generalizable. String.h contains a set of memory operations which are very highly similar to the operations on strings previously discussed. Rather than accepting char star pointers, these functions use void star pointers, so you can pass it any type of pointer that you wish. You can do integer pointers, you can do double pointers, you can do pretty much any type of pointer that you want. So if you want to concatenate an array, 2 arrays that contain integers, you can use something that is extremely similar to string cat, except it would be memcat, or something like that. At any rate, this type of stuff, if you Google around, you'll be able to find it very easily. So there we go. Questions. Ask me questions. Oh, we had 12 people there for a second. But then they left. Awesome. Like, one of the things I really, like, one of the reasons that C is one of my favorite languages is that the rules are very simple, but they're not, like, if you understand the deep rules, everything makes sense. Like, if you understand pointers, everything that we're talking about right now makes perfect sense. Right? It's like, if you you will improve as a C programmer with your ability to think as the computer thinks. Right? And by learning how to program C, you are learning how the computer actually thinks, right? So, yeah. Hopefully this isn't too bad. Sorry, give me 1 second. Gee, I hope I'm not coming down with something. Dun, dun, dun. All right. Formatting. String formatting. If you pay attention to this section, you can accomplish this question in about 5 or 6 lines of code. If you do not pay attention to this section, it will take you probably over 100. And over 100 lines of code are much more, like, the more code you write, the more bugs you probably put in it accidentally. So, up to this point, we have only briefly touched on the advanced features of the string formatting tag %. We will discuss now the following features: rounding of floating point numbers and displaying of specified numbers of decimal places, aligning columns of numbers, right and left justification, exponential formats, and fixed field widths for various data types. All of the following formats, all of the format specifiers we were talking about are used in printf, scanf, and their cousins. You know where these are used by now, and the fun thing about printf, scanf, and their cousins is, if you, like, as we demonstrated, snprintf is a printf cousin, so you can use this for snprintf. We are going to see when we do file I/O that there's a scanf function, a scanf cousin that reads files, and these format tags are applicable there as well. Okay, so we've got formats. So we know our basic format conversion specifiers. D is, of course, signed decimal integer. I is signed decimal integer as well, but they differ when used with scanf in some way unspecified. O is octal. U is unsigned decimal integer. X is hexadecimal integer. H, L, or LL, that these guys can be placed before any one of these to specify the length. These are length modifiers. They say, okay, it's a D, but it's long. It's a long D. You put it to L, and then it becomes a long D. So, printing integers in various ways. This will be the example.c that I had. Get it? Example.c. Yes. Maybe? No, this isn't it. Okay. Well, I've got the output here anyway. So I could enter this into it, compile it, and then show it to you, but I could just also use the output, which is displayed in the slides. So if you don't mind, I'm going to not live code this one. So printf for d and I prints the same, plus this number minus this number. You get no plus sign, but you do get a minus sign. That's because the plus doesn't really exist. HD is a, what is it? Short. That's a short integer. LD is this long number. So in order to get a number of that size, you have to put the L suffix on it to make it a long literal, which is probably something that you haven't had to do before, but you know, that is what it is. O is octal, so in octal this is actually 707. Unsigned integer prints the same. Printing a negative number as an unsigned integer is interesting. And of course, x is hexadecimal. So without going into too much depth on it, the way that negative numbers are stored is in a format called 2's complement. And effectively, the way that it works is, well, actually, we can do a quick example. Get it? Yeah, okay. So if I print f, I think it's easiest to print this off as a hexadecimal. So 0. I'm going to use a loop because I'm a programmer, gosh darn it. For int I is equal to -10, I is less than or equal to 10, I plus plus, print me the value. Or, wait, this is example.c now. Oh, yeah, I have to print I, don't I? There we go. So this is how 2's complement works, right? 0 is 0. Positive numbers are what you would expect them to be. But the negative numbers, -1, is all of the bits in the numbers flipped to 1. That's what F is. Do I have a binary conversion? I wonder. No, okay. There's probably a format tag for binary. C format specifier binary. Should be one. Stack Overflow. Yeah. There isn't one. Okay. Well, okay. So, I guess we're just gonna have to make do then. So F means 4 bits all having a value of 1. E means 1110. D means 1101. C is 1100, etc., etc. So you can see it's counting backwards from the maximum value that the integer may have. That's 2's complement format, right? So if you print an integer as an unsigned integer, but it's negative, it'll treat it as if, like, it'll treat that value as if it's correct. You know, it'll treat it as if it were an unsigned value, even if it's not an unsigned value. And that means that it'll print off, basically you'll get some really big numbers if you ever try to print anything negative. And that's how numbers work. So, if you wish to print some floating point numbers, you can either do fixed point or exponential notation. So, and, you know, a lot of these you can do either way. So it's just the difference between, you know, printing it with decimal places or printing it in scientific notation, right? That's the only difference. The plus doesn't print, the minus does. The default is to print 6 digits to the right of the decimal point, regardless of how many there actually are. And the difference between uppercase and lowercase is that you just print it with an uppercase or lowercase e. So there you go. Floating some ideas. E and F will show 6 digits of precision by default. F will always print at least 1 digit to the left of the decimal point. G will select E if the exponent would be greater than the specified precision, or less than -4, and F otherwise. So G it just selects between E and F depending on how big or small the number is, and you know, it's like print it for me in a manner that makes more human sense. You don't get much of this in C, so it's important to appreciate it when you get it. E and G display rounded values. F displays truncated values, right? The difference between rounding and truncating, right? We know the difference between rounding and truncating. If you round a value, then if that value, like if you're rounding to the nearest whole integer, if the partial, like if it's 5.7, it gets rounded up to 6. If it's 5.2, it gets rounded down to 5. Truncation, in truncation, it doesn't matter if it's 5.9999999, it'll get truncated to 5. It must have achieved full 6hood in order to be 6. Yes. Note, if you want to actually insert the percent sign character, you have to use 2 percent signs. Cool. So, I am assuming things are going well so far. We actually need to keep moving. So, working with field widths. Have you ever been bummed out because getting C to print a table of values with properly aligned columns is hard? Fear no more. Inserting an integer value between the percent sign character and the format specifier sets the field width. Data will normally be right justified within this field, although you can set that. Field widths may be used with all format specifiers. If your field width is too narrow for the data will overhang the specified field width rather than being truncated. Field widths. So, if we have a field width of 4, right, for all of these integers, this is how it prints out. It allocates 4 characters for the printing of that number, which and right aligns them. So it's kind of like using tab, except it eats into the tab, I guess. If you have more than 4 characters, it will overhang, and more than 4 characters includes whether or not a negative sign is printed. We can specify various things for different data types using the dot format tag. When applied to int, leading zeros are included instead of spaces to fill the gap, to fill the field width. When applied to floats, this controls the number of decimal places that are displayed, i.e. the precision. So replace x with some number. When applied to strings, this sets the number of characters to display. The rest of the string will be truncated. Incidentally, the S tag looks for a null terminating character when it looks for a null terminating character when it prints, right? It's like, print this string. Okay, I expect it to have null termination. If it doesn't have null termination, you can produce a segfault using this formatting tag, which is funny because normally we think of segfaults as being caused by like array out of bounds things that we've done with if statements and loops and that sort of thing. But we can actually achieve that with this %s as well. Using %s instead of %c can also cause it. So if you mean to read a character, but you read a string instead, that can cause segfaults. Specifying a field width is an effective countermeasure against non-null terminated strings. So it is safer to specify how much of the string you can read. So here we go. Printing integers and floats and various things. So you can see we've got an integer with 0.4 here. We've got an integer with 0.9 here. A float with 0.3, printed in various formats, and the string happy birthday, which is printed with 11 characters. This is how that looks. So we've got 4 characters. It's 0. It's got 0 ahead of it. Precision has been specified to 3 decimal points, despite the fact that this float has 5 decimal points. And of course, we are truncating the string. It says happy birth instead of happy birthday because happy birth is 11 characters. Depends on the birth. Field widths and precisions may be used together. So you can have you can specify 9 spots for a number that holds however many digits of precision. The underscores here are meant to visualize the spaces. So, how are you guys doing so far? Well, actually, nope. This is the last slide for this one, so I'm gonna say it. I'm gonna go through this slide, and then I'm gonna ask for questions. But get your questions. You can start typing your questions now. And send them, please. Various options. In addition, there are a number of flags that may be included to modify the print format. If you include a minus sign, that left justifies the output. A plus sign displays a plus sign on positive values and a minus sign on negative values. That's particularly of interest if you're doing anything with accounting. Typically, when you're doing accounting, you want to see the plus signs, right? But, printing a space before a positive value. So space, if you put a space in there, that prints a space before a positive value, which just helps you align your text. So, basically, these two would be the same because you'd have an extra space instead of the not negative sign. And 0, if you put a 0 in there, that pads the field with leading zeros. there are various options. But, yeah. Memcopy. Okay. Let's see here. Memcopy. Okay. So let's say we had I have it open in another window where? Oh, here. Okay. There we go. All right. Good Lord. Int x is 1, 2, 3, 4, 5, 7. There we go. And int y is, we'll just assign it, we'll give it 10. Memcopy. Gonna have to look up the usage. Memcopy. So it's source, destination, and size. So it's, where are we here? So destination will be y, source will be x, size will be 10, and then printf. Actually, can I do this in, I think I might be able to do this in Python Tutor. Or I guess it would be C Tutor, wouldn't it? Python Tutor. Gets me every time. I teach too much Python. So, there we go. There we go. Memcopy. Oh! Okay, so that must be, yeah. Okay. So it has to give me, I have to give it the size in bytes, I guess. So 10 times size of int. Memcopy is probably agnostic as to what data type. There you go. Everything's copied. So there you go. Cool. So, remember kids, don't drink and code. This is the worst spaghetti code I've ever seen. The comments are useless. There's variables that do nothing. What depraved madman wrote this? Wait, I did this 2 weeks ago. That is life, my friends. On the big blue marble. So, let's talk about file operations. The following 5 functions are essential operations for reading to and writing from... Wait, strike that. Reverse it. Files. Reading from and writing to. You've got fopen, fclose, fscanf, freadf, fwrite, fprintf, and fendofile. Foff. Using these files requires knowledge of the file structure, which is defined in standard io.h. So by including standard IO, you have included all of this stuff as well. Think of it as a structure containing all of the information relevant to a file that is currently being streamed. So internally, a file, a struct, I know we haven't talked about structs, but a struct is just a way of collecting variables together. Basically, there's this thing that keeps track of all of the stuff, like where you are in the file, what file you have open, all that kind of stuff, that is produced. This will probably make more sense when we cover struct next week. This section assumes you at least vaguely remember how to do this in Python. So if you don't remember how to do file IO in Python, review it, watch this bit again, okay? So, opening a file stream requires an invocation of fopen. So, to open a file, it actually works pretty similarly to Python. As you may expect, this is the file name. Incidentally, all of that business I was talking about with including the full or relative file path to the file, that is also applicable here. That's the name of the file to be opened. The file may be specified by either absolute or relative addressing. And mode is a string specifying, among other things, whether the file will be opened in read or write mode. This is actually the exact same as how things work in Python. The output of this function is a file pointer to the data stream object. You don't have to worry about direct manipulation of this pointer. It is only interacted with via file operation functions. All you have to do is keep track of it and pass it where it asks for it. So here are your modes. R is read mode. W is write mode. A is append mode. R+ opens an existing file for updating. W+, create a file for reading and writing. If the file exists, discard current contents. So this is overwrite. And A+, open or create a file for reading and updating. All writing is done at the end of the file. This is, yes, again, an append operation. In general, you probably will only need to worry about reading and writing. F-close, but no cigar. Wah! There are some bad puns coming up. I hope you're ready. Just as dynamically allocated pointers need to be freed when they are no longer needed, a file stream must be closed when you're finished with it. You have to tell the operating system that you're finished with the file. You just have to. Otherwise, how's it going to know? This one's pretty straightforward. It takes the file stream as an argument, returns 0 on success, and EOF on failure, which is a non-zero return value. F-close. F-open, F-close. F-scanf is difficult to write a pun for, so I skipped it. If you want to treat your file like you are reading information from standard input, consider using fscanf and fprintf. So you can essentially work these things like their standard input and standard output. If you're comfortable, if you're used to working with standard input and output, which you likely are because that's all you've been expected to do so far, these are probably good functions to start with. Because the usage is exactly the same. Right? The only difference is that the first argument is the file stream, right? This file stream object that you created when you opened the file, you have to pass that in as the first argument, and then after that, it's just scanf, right? While the first argument is the file stream we are reading from, the rest of the arguments are used exactly like scanf. The return value is the number of input items successfully matched and assigned, i.e., the number of format specifiers in the format string that were successful. So there you go. So, again, scanf has much more, like, scanf is much more flexible than you may think it is, right? Like, if you're writing something like scanf, if you can include characters that aren't the thing you're being read, right? That's being read. So, like, if you include, like, exclamation point, and then D, right? Then printf int I address of I, then print me the thing I gave you, right? Is this convert example? GCC example.c B. What's B? Get out of here. A dot out. If you just enter 5, you get something weird. But if you enter it the way that it expects it, then it works. I don't know why it didn't register the first time. But anyway, oh, yeah, because it's scanning for a new line. Stupid. I need to recompile it. There you go. So you can, like, there's a question where you have to read dates, and the dates have, like, slash characters. So I hope you know now how to interpret those. Anyway. Yes. fprintf works in pretty much the same way as fscanf. It writes characters into a file in exactly the manner what you would expect. The first argument is the file stream. Everything else is exactly the same way as you've been using printf so far. So there you go. Fread any good books? Fread any good books lately? Haha. So if you don't want to loop through a whole bunch of scanfs, if you'd prefer to write the entire file into memory all at once, fread will do that. So you need a pointer, you need a size, you need mem and nmemb, which we'll talk about, and you need file stream, the file stream object again. Pointer is a pointer to the block of memory that you're writing to. It needs to be at least as big as size times nmemb. Size is the size in bytes of each element to be read. Using size of here is a good idea. So size of integer, like, are you reading integers? Are you reading characters? You got to tell it what the data type is, right? This is how, like, someone else, like some other programming language, would expect you to specify a data type here. Because this is C, it doesn't care about data types. It just cares how big is the thing, right? So whatever the data type of pointer is, you should put size of that data type here. nmemb is the number of elements to read, each the size of size. And of course, stream is the file stream. fread returns the total number of elements successfully read. Fwrite to remain silent. And in reverse, you can write the entire contents of a piece of memory into, a file in pretty much the exact same way with the exact same usage. Pointer is the pointer to the array of elements to be written this time. Size is the size in bytes of each element of pointer. nmemb is the number of elements to be written. Stream is our old friend, the file stream. And fwrite returns the total number of elements successfully written to the file stream. So you can see these guys operate in pretty much the same manner. Whew. FIOF World Cup. That's a joke about soccer. So, all this reading of files is fine, but how do we know when we're finished? So this is an important one if you're using the scanf method, right? Rather than the fread method. So, FIOF, file stream, all that does is it checks to see if the file stream has reached the end of the file. In Python, your for loop just handles this for you automatically, but in C, nothing comes for free. You have to know, so basically, you could do something like write a while loop, make the condition this guy, and, or make the condition not this guy, and then put the scanf inside that loop, and that would loop through the entire file until the end of the file is reached. Output is non-zero if the end of the file has been reached, 0 otherwise. There we go. And we have an example, so let's do an example. Get it. Let's see, do I have one? Get it. io.c, sure. Include stdio.h. Int main. So let's just start by reading in a file and printing it to standard output. File handle, so file star file handle is equal to fopen. I think I've got a list here, clients.txt. Yep, good. So we've got clients.txt. We shall open that in read mode. Ta-ra. We shall have a intermediate buffer that contains 100 characters, just for managing stuff, while not file end of file of file handle fscanf string limited to 99 characters, let's say. Give it the address of buffer, and give it, of course, the file handle. And then all we need to do is printf buff. No, like this. You fool. There we go. Buff. Let's see how badly let's see. I seem to have done all the semicolons this time, at least. gcc io.c. I don't need to use the address of operator. There we go. A.out. I need to include new lines. There we go. So that's kind of interesting. So this is splitting it up on white space. So let's yep, let's make a few buffers, and let's take a look at that file again. So it's a integer, then a string, then a float. So we can do an integer, a string, and then a float. Yes. And that will be buff1. But these will be, in that case, this would be an integer, buff1, and this would be a double, buff3. Buff1, buff2, buff3. And then let's print them in a different order, using different things. Just to show that we can manipulate the data. And of course, need to include the ampersands. Let's make that a float rather than a double. Float. No complaints. Run the program. Cancel that. We've done something foolish. What have we done that's foolish? Did we get any correct output? Try limiting that. No, that's not. Very strange. Oh. I think I might not be adhering to the actual, what the file looks like very well. That might be it. Yeah, okay. Let's try, I think I've got characters astray. Yeah, these commas don't exist. It's trying to match something that doesn't exist. There we go. Ta-da! So if I were to edit the client's file, for example, and make it so that, you know, these were hyphens, maybe a little more complex. And every line had this guy at the end of it. Right? You know, something a little bit different. If I match that inside of the string itself, if I've done it correctly, then it still works. Right? And that's it. That's everything. Computer science may discover immortality, but it won't happen in the next 80 years. This is the well of uncomfortable truths. You'll never find a programming language that frees you from the burden of clarifying your ideas. But I know what I mean. Yes, that is the problem people have with programming languages. Anyway, questions. Do you have any questions for me? Does that work? Seems to. Awesome. How hard is the lab today? It's easier. This lab is easier than the last one. A lot of it is doing some stuff on GitHub that hooks in with the stuff we've been doing about makefiles and shell scripting. Basically, how to run like makefiles and shell scripts automatically within GitHub as well. As long as you're not like too intimidated by configuration files for things that you haven't been taught in the lecture, it shouldn't be too bad. Specifically, like, if you don't follow the instructions correctly, GitHub will tell you which instructions you've done wrong, and then you can fix it. And, like, please... So, one thing about it, though. Please do actually read all of the stuff that GitHub displays for you. If you use diff and the files are identical, will anything come out? Let's see. CP clients. I don't think so. Text to clients 2.text. Diff. Diff. Nope. Doesn't output anything. You can check that kind of stuff yourself, too. Just don't be afraid to experiment, eh? Literally every single one of the best programmers self-taught. Okay? So use your powers of intellect to find solutions to questions. Oh yes. Yes. So this guy and this guy, yeah, okay. Let me do that now. I won't do that on stream. I'll let you guys go, but I will do that right now. All right. Take her easy, folks. Have fun with the lab today. Don't do anything I wouldn't do. Bye-bye.